Good evening, everybody, and good morning to our friends the other side of the Atlantic. It's great to see William Reeves with us this evening. He's a good friend of this forum and always has something interesting to share. But just before we get into that, I'd like to, is Andrew Thomas on the call?
I'm here.
Ah, excellent. Yes, yes, Andrew's going to introduce, I'll just say a few words about a forthcoming training tutorials that we're planning just before we hand over to Whit. Andrew.
This is something that grew out of discussions about muon detectors, and people seemed quite keen to learn a bit more about how to collect the data and what to do with it, other than just recording it onto a SD card in the device itself. So we've organized a set of 4, possibly 5, 1 hour, nominally, depending on whether we get good questions, introductory sessions as to the use of Python and the Raspberry Pi. The first one will be on Monday week, which is the 15th of April at 1900 British summertime, which is 1800 UT. I'll let you work out where you are in that. The idea is to start from absolute basics, so the presumed knowledge of anybody wishing to join in is that they know how to basically install some applications on Windows, beyond or a Mac if you must. And beyond that, we're going to start right from basics: how to get your Raspberry Pi going, how to operate it in a headless mode, how to transfer some Python scripts onto it, and how to run them. That'll be the first session. Beyond that, the idea is, with Rupert Powell's help, to run some sessions on writing your own Python for reading data from the muon detector, writing it onto a disk, and then archiving it, processing it, and doing some basic data processing. And that should take up about sort of, say, 4 or 5 hours over 4 or 5 Mondays. If anybody thinks that that hits their level of knowledge, you'll be very, very welcome.
Yeah, thanks, Andrew. Excellent, excellent. Okay, as I mentioned earlier, we've got Whit with us this evening, and with no further waffling from me, over to you, Whit. Our monitors are yours.
Okay, thanks, Paul. Thanks for calling me back to do this. I thought that the last time I'd tortured you guys so much that you were never going to talk to me again. So I'm going to make another attempt at that. Let me share my screen. Hopefully you can see full screen now.
Yep, looking good.
Okay, excellent. Okay, well, this session is going to be about the solar eclipse last October. And what I did is I set up some VLF receivers at one of my observatories. I also set up a whole fleet of HF receivers. And I discovered the hard way that when you produce a lot of data, it takes a lot of time to process it. So I'm just going to focus on the VLF part of it. And I was particularly interested in the effects on propagation. Now, interestingly, this background image that I have is actually a heat map of all the total solar eclipses over a 5,000-year period. And you can see that if you live long enough, no matter where you are on the planet, and it makes sense that you'll eventually see a total eclipse. So this heat map is kind of fun to look at, and it's also interesting to note that there are some hot areas.
Wait, can I just interrupt? I'm seeing you full screen. I can't see your presentation.
Okay, are you the only one that has that?
Yeah, I can see the full presentation.
So can I.
So can I.
Okay, well, I'm going to try and fix my own problems. My apologies.
Yeah, you might try logging out and logging back in. But yeah, it apparently isn't anything that I've done wrong.
Okay,
At least I
my
hope
apologies.
Not yet.
So I've got quite a few slides to go through. I got some introductory comments. The statistics of the eclipse last October, what I was expecting to see, a little bit about the receiver and transmitter stations, and the instrumentation that I used. And then I've got some slides on the results, of course, and a little bit of discussion, as well as the future, which is Monday. So there's one type or another eclipse every year on average. And this covers partial eclipses, total, annular, and so on. The eclipse of last October was an annular eclipse, which I'll talk about in just a minute. But what happens during eclipse is that the sun's radiation is blocked by the moon, and that changes the characteristics of Earth's ionosphere, and in turn that would affect radio propagation through that part of the ionosphere. So and that's particularly what I was interested in. Now, it's also well known that the sun's visible light, as well as its radio emissions that are detected by an observer on Earth, are reduced as well. But I'm not talking about that part at all. I didn't look for the direct effect on the solar emissions, only its effect on the ionosphere. So here's some statistics. And this image shows the total and annular eclipses from 2021 through 2040. And the one that I'm going to be describing today is this red line right here that starts up in the northwest, or actually the northeast part of the North Pacific Ocean, and then goes down through the U.S., Central America, and over the top of South America. So partial eclipses aren't shown here. This would be an extremely busy graph if it showed the 40 or the 20-year period for every type of eclipse that there is. Now, this image here is produced by a fellow, Fred Espenek. And Fred, I apologize to you if I mispronounced your name, but he's produced these plots for every solar eclipse from now almost to infinity. And they're published on NASA's, the Goddard Space Flight Center, NASA website. And it tells you almost everything that you would want to know about any given eclipse. And in particular, this is the one that we're concerned with, the one in October of 2023 on the 14th. And it gives you the first contact, the final contact, the greatest eclipse, the maximum, and all of that type of information. So if you're interested in any eclipse, this is the place to go to start, I think. Now, what happens with this particular eclipse is that the path was diagonal across North America. It covered, actually went down into South America as well. And it was theoretically visible from some parts of Alaska, but the main path didn't cross it. But that didn't really matter to me because I was more interested in propagation of VLF stations to Alaska and not particularly what was happening in Alaska. So this shows what my observatories are, or where they are with respect to where the eclipse was. Now, this red band that you see in the middle here, that's the actual eclipse path. And then progressively, the area that's shown here would be the area seen by, would be a partial eclipse seen by observers on the ground. Now, I have 3 observatories in Alaska. They're all kind of clustered here in the southwestern part, but Coho, the one right here, is the only one that I had the VLF receivers running at. I did have HF receivers running at Harp, Anchorage, and Coho, but only VLF at Coho. So that's what I'm talking about today. I'm going to turn on my, let's see, spotlight here. So you should see my cursor. So let's see here. There we go. Now here's an image or a animation that NASA put together that shows the path of the of this eclipse as it moves from the North Pacific down through South America and beyond. This is another thing that NASA has done, is they've produced these animations for just about every eclipse that is in the livable future. So again, you can go to their website and download these images. They have huge tables of eclipses for you. So during an annular eclipse, the sun, moon, and Earth all line up, but the moon is actually too far from Earth to completely block the sun itself. So what you end up with is a bright ring around the moon, as seen by observers on the Earth when the eclipse is at its greatest point for your location. Now the first contact was at 15:03 UTC, and this was 7 o'clock in the morning in Anchorage, and so it turns out that the sun was still below the horizon here, but there was propagation paths from daylight into Alaska during this, even when the eclipse first started. The greatest eclipse, or the maximum, was at almost 1800 UTC, and the last contact was at almost 2100. So there was an elapsed time of almost 6 hours there, and I actually set up my recordings to operate an hour before, through the eclipse, and an hour after. So I have a total of 8 hours of recordings. Here's a couple of images that were taken by NASA cameras. One was in Albuquerque, New Mexico, at the time of the greatest eclipse, and that's shown in the upper left. And then at Kerrville in Texas, showing exactly the same thing, but at a different geographical location. So what was I expecting? Well, at the time of this eclipse, the sun was getting pretty close to the peak of its sunspot cycle. So I was expecting to have some complications due to that because of solar phenomena like radio bursts and things that could affect propagation and almost looked like the eclipse itself. So near the peak, you have a lot more stuff going on in the sun. You have radio bursts, a lot of transient phenomena. These complicate the observations. Now at VLF, the primary mode of propagation is either ground wave or a space wave. Now the ground wave doesn't get very far, but the space wave, which is a waveguide mode, actually does. And that's shown here. So if we have a VLF transmitter over here on the left, you get radiation that may go up into the ionosphere. It may follow a space wave, which is the waveguide mode that basically uses the D region of the ionosphere as the upper wall of the waveguide and the Earth as the lower wall. Or you have a ground wave. Now, the ground wave peters out pretty quickly, so you don't get that. You're not able to receive that at any great distance from the transmitter. So this is the primary mode for VLF type transmissions. Now, another complication is that this particular eclipse will occurred about the time of, or actually before sunrise in Anchorage. And so you have the sunrise and sunset effects that could affect your observations at VLF. And so this is yet another complication. If the sun radiation reaches the D region, then you have absorption. So there's a lot of complications that will kind of reduce the quality, I guess, of your observations. There's a lot of variables. I mentioned sunrise and sunset. You have just the things that go on in the ionosphere. For example, up in the upper regions of the ionosphere, you have these traveling disturbances, ionospheric disturbances that are happening all the time. Those will complicate your observations. As the eclipse shadow moves across the Earth, it changes the ionosphere, so that its effects will vary with time and position. Wind and turbulence in the D region are going to affect variability. Earth's magnetic field is going to cause could cause some effects, and in particular in Alaska, the inclination of Earth's magnetic field is pretty high. At Coho, it's 73 degrees, so you're almost vertical there. But again, the propagation is coming from some other place to Coho, so I wasn't really expecting a whole lot of magnetic variation in these particular observations. You also have your space weather effects, coronal mass ejections. Those are delayed. So if there was a CME a few days before the eclipse, maybe it would collide with Earth's magnetosphere during the eclipse. That's going to really goof things up in terms of observations. Solar wind parameters, the density and the wind speed and so on, have a significant effect on Earth's ionosphere. So we have all of these complications. And I knew all of these going in to this eclipse. So I was really not expecting a lot of really good results, but I'll show you some here in just a minute. So the receiver sites, just to remind you, this is Alaska, and Coho Radio Observatory is the one down here in South Central Alaska that I actually had the VLF receiver sites going. The distance from Harp to Coho is about 400 kilometers, and from Harp to Anchorage is about 300 kilometers. So there is roughly a 100-kilometer distance between where I live and where the observatory is located. Now, the transmitter stations that I looked at, I'm able at Coho, I'm able to receive actually somewhere in the neighborhood of about a dozen VLF transmitters. And so I went through in a long process, long before the eclipse, trying to figure out which one of these would be the best to monitor during the eclipse itself. So I ended up with Northwest Cape in Australia at almost 20 kilohertz, all the way through to Colorado at 60 kilohertz, and roughly scattered in between there. And the distances varied from a couple thousand kilometers away for the transmitter up to almost halfway around the world for the one in Australia. So this shows an overhead view. This would be above Coho, and the direction of the transmitters that I selected. So I had one in Japan, which is almost exactly west of Coho. Northwest Cape is almost exactly west of Coho, and NPM in Hawaii is almost exactly south. NLK in Washington State in the contiguous US is more or less east of Coho. So I used VLF loop antennas, and they're directional, so I had to do some compromising on the way that they were pointed. Now, I did one of these plots shown here for every one of those stations. And this one is a plot. This plot shows it's a world map. Here's Coho up here in Alaska. And this is the propagation path, the Great Circle propagation path to Northwest Cape in Australia. Now, the short path would go to the west and then down like that. And the long path then would go to the east and then down and over to Northwest Cape. And you can see that the eclipse path shown by the black line here actually crossed that long path. And this yellow dot right here is the sun at the time of this plot, which is I made at the middle of the eclipse. So the red dash line that you see, that is the total area where you would see at least a partial annular eclipse in this case. So that's for Northwest Cape. And I did one of these for Hawaii, and you can see that the short path is actually relatively short. It's about 4,400 kilometers. And the eclipse started right up here, almost directly in line with that short path. And then the long path, of course, goes the long way around. This is JJI in Japan at 22.2 kilohertz. And they're directly to the west of Coho. And like Northwest Cape, the long path then did cross the eclipse, or the eclipse path. So that I was kind of encouraged that maybe if I did see any long path propagation, then maybe that would have some effect on it. And then NLK in Washington is relatively short. It's only a couple thousand kilometers away. Its long path also crossed the eclipse, and but its short path was in the within the influence of the eclipse itself and roughly paralleled the eclipse path. And then the last one is WWVB, which is a time frequency station at 60 kilohertz. It's in Colorado, shown by the blue dot here. And you can see that the short path between the two stations roughly parallels the eclipse path. And then the long path actually crosses it about midway. Now I have marked on here 1015 megahertz. I was also monitoring WWV on those frequencies, but I'm not talking about those here. A little bit about the instrumentation. I'll just say one more time that I was looking at VLF. I did take observations at HF. They're not included here. The VLF sensing mode that I used was received signal power amplitude only. I did not look at phase. In fact, I wasn't set up to do any phase analysis. The receivers that I use are shown here and some of the characteristics of them. I used an RSP Duo, which is made by SDR Play, and I set up 4 virtual receivers 0 through 3, and those were used to monitor the VLF communication stations. And then I used an RSP-DX to monitor WWVB in Colorado. And I set them all for, I used the 2 megahertz basic sample rate, but then I used a 32 times decimation. So that brought the effective sample rate down to 62.5 kilohertz. These are 14-bit receivers, and I use a square loop, which I'll show in just a minute, on with the RSP Duo, and I had a round loop, a separate loop that I used with the RSP DX. Now these antennas their effective height seems like they're awfully small, a couple of centimeters, and so that implies that you need a fairly large signal strength in order to get anything useful out of it. And but it turns out that these antennas, even though their effective height is not very great, they seem to work pretty well. Here's the square loop over on the left-hand side. It's up about 3 meters above ground, has a channel master television type rotator, and that's controlled from within the observatory. And again, it's the RSP Duo. I use 0IF mode for all the VLF stuff that I do. And then I also use the SDR Uno software, which is the native application software for this particular receiver. And this gives you a little bit more detail on the passive loop itself. It's this is shop built. I built this back in 2009, but it turned out I didn't actually deploy it until just a few years ago. So it's a 1.2 meter diagonal, 64 turns, 4.5 ohms resistance, and it has a self-resonant frequency of 46.5 kilohertz. And I rotated it 60 degrees from true north, and that gave me a compromise so that I could receive both the westward and the eastward stations that I was looking at. The WWVB was looked at with this round loop antenna shown here on the left. I actually use a Yaesu rotator on that one and a controller back in the observatory itself. The RSP DX is a pretty good VLF receiver. Again, I operated it in the 0IF mode, and I used the native SDR Uno application. So I was actually running two instances of SDR Uno, one with the SDR RSP Duo, sorry, and another instance with the RSP DX. This shows the loop. It's a Hewlett-Packard loop from the 1960s that I resurrected and refurbished a few years ago, 1.2 or 1.1 millimeters in diameter. It's got a self-resonant frequency of 96 kilohertz. And in fact, the same loop was used for 75 kilohertz applications back in its day. It's an active loop. It has a balanced amplifier in the base of the antenna over here, and it operates off of 24 volts DC. I rotated it to point toward WWVB, which was 104 degrees true north from Coho. Now, these receivers and antennas are all really handy to have, of course, but nothing works unless you have some infrastructure to support it. So you have to have DC power supplies. I use network time protocol servers to keep the PC time really accurate. I use rotators to point the antennas. I have UPS to attempt to protect the rural system in Coho from power transients and outages and so on. There's a local area network. I use AT&T 4G LTE service as my for the wide area network WAN service, and I have a VG 5530 cellular modem shown down here on at the very bottom. Now it turns out that modem just recently failed on me, and so I replaced it with a Digi International unit that is in operation right now. Now, the last but not least, in terms of instrumentation, is you have to have a good PC running. And I use these Lenovo small form factor PCs. they've turned out to be super, super reliable. And they actually have real line-in audio ports. They can be equipped with real native EIA 232 serial ports and so on. Now, it turns out that Coho is not heated during the wintertime, so that inside temperature can get below zero. And it turns out that I have had failures. I've had some RAM failures within the PC because of the cold temperatures. I've had a solid state drive, this PCIe unit. I had one of those failed. Solid state drives may drop out, and they won't work until they warm up, but they do come back to life, or I've had that happen where they do come back to life. But the PC itself has been super, super reliable, and I've had no problems with them whatsoever. Of course, Windows 10. I have it locked down to prevent it from doing its random updates that really goof up any kind of dedicated observations. Okay, so now that we've gone through all that, let's look at some results. The plot that I'm showing here has all of those 5 stations, or actually these are the 4 communication stations overlaid. And so it's really busy, but I'll show you some individual plots here in a second, but let me show you what the key is to these plots. This shaded area that you see here, this gradient type blue area, that is where the eclipse occurred. So the beginning is the left dotted line, blue dotted line over here. The end of the eclipse is the right blue dotted line over here. Local sunrise is the dot dash line, the orange dot dash line here, just to the left of middle. That was around 1640 something in the morning, or in the UTC afternoon, which was morning in Alaska. There was a C 3.5 solar flare that happened just before sunrise at Coho, and I've placed an arrow that shows that. And if you look at these, you'll notice that there's some little burble over here on the right. I don't know what that is, but I'll talk about that in a little bit more in detail here as we go through each of these plots. So here's the one for Northwest Cape in Australia. And again, the eclipse boundaries are shown over here on the left and right by the blue dashed lines, and local sunrise at Coho, the orange dot dash line, and the C 3.5 solar flare. So when I looked at this plot, I didn't see anything obvious that had to do with the eclipse itself. I can see some, there's always effects at sunrise and sunset on VLF paths. So I couldn't distinguish, or I wasn't able to distinguish anything eclipse related to the way the signal level from Northwest Cape actually was received. But there is some interesting phenomena going on over here. On the right, you can see a periodic structure. And the period of this is what, roughly an hour or so. And you see a little bit over here on the left as well. This would be before sunrise at Coho, and would still be darkness in the path, on the westerly path to Northwest Cape. So those are interesting. I don't think that they're related to the eclipse, but they're kind of fun to ponder. Now, the plot that's shown here is NPM in Hawaii. This is the one that's almost exactly south of Coho. And you can see a sunrise effect here. You don't see any effect from the flare at that was before sunrise. There's nothing obvious here that says, okay, this is caused by the eclipse. nothing is jumping out of the plot. But we have this burble over here on the right that is kind of interesting. I don't think it's eclipse related. It could be, but I'm not going to commit to that. The first contact at about 1500, so the short path and eclipse were almost intersecting at about 1500. So that would have been right here at the very top. There's nothing going on there. So I don't see that there's any eclipse effects at the beginning. Here's the Japanese plot, and Japan, the short path would be almost exactly west of Koho. And you can see what I think are sunrise, sunset effects here. The eclipse began over here on the left and ended over on the right. Again, there's some periodic structures here, and there's a real deep null at 1920 or so, 1915, and another one about an hour later, a real deep null there that I can't explain. And whether or not these are related to the eclipse, I don't know. But again, they're fun to ponder. And if I have not noticed these on non-eclipse days. So I'm going to go back and revisit this after the eclipse on Monday and see if maybe I can do some correlation there. Here's NLK in Washington State. This is a really relatively short path, couple thousand kilometers. They're more or less east of Koho. And again, there's nothing here that jumps out at me except for this burble over here on the right that coincided with the one here in Hawaii. Oops, sorry, I jumped over it there. So in Hawaii, I saw that, and in Washington, I saw that at about the same time. So that could have been some other phenomena that caused that, but I'll be on the lookout for that in future eclipses that I look at. Now here's WWVB. This is almost due west of Koho, and it's kind of a noisy plot, but here's again the flare. Whether or not this is caused by that flare or not, this jump in signal level here, I don't know for sure. It was before local sunrise, but the path from Colorado to Koho was almost all in daylight. So that flare could have caused that peak. But again, there's nothing here that I can say is, okay, this is exactly what I was expecting to see from the eclipse. But I do see a periodic structure down here again in the afternoon, and or in the later part of the eclipse. So you can see that there is with about a 1 hour period roughly, the long path from Colorado crossed the eclipse path at about 1730, which would have been right here. Nothing obvious there, but there was a dip and then a peak, and but whether or not that's eclipse related, I really don't know. So let's have some discussion about this. It turns out that because I didn't have anything definitive, there's not a whole lot of discussion. But I do realize that the coincidence of the start of the eclipse and sunrise could have disguised some propagation effects that were caused by the eclipse itself. So the timing may not have been the best for that eclipse in terms of sunrise, but that I hope to prove that one way or the other with future eclipses. So in terms of this particular October eclipse, the sunrise was within a couple hours of local sunrise. So anything to the west might have been affected by the eclipse. Anything to the east, anything to the east might have been affected. Anything to the west probably wasn't because it was in darkness. But who knows? We'll find out hopefully with future eclipses. So the primary results from this study would be the statistics at specific frequencies in the VLF and LF bands. So I'm going to continue using those 5 stations that I listed previously, and hopefully I'm going to gather some propagation statistics over the next eclipses that I am able to observe here in Alaska. So what does the future have to hold? Well, as we were talking about earlier, on Monday, we've got an eclipse. It starts at 1542 UTC out in the Pacific, mid-Pacific, and then flows up through Mexico and into the eastern part of the US and Canada, and then gets over and almost touches the UK, and pretty much is done by 2052 UTC. So this path here, what I'm going to do is I'll use those same stations, and I'll plot out the long and short paths. And it looks like at least some of them are going to cross the eclipse will cross these propagation paths to different locations. So maybe this next eclipse, I'll get better results. Now, there is another thing that I wanted to mention, and that is for the Monday eclipse, is that there's been a D-Light station. This is a scaled back long wavelength array station, has 4 antennas. They're set up as an interferometer, and Olivia Young is down in Hawaii, has set up this station in Ohio State, and it is located right along the eclipse on Monday and the total eclipse on Monday. And she's put together this, it's almost like the LWA TV. It shows the sky image, and it's going to be live, so you'll be able to see the sun move and across the screen and so on. So if anybody's interested, I can post this web link in the chat, and I really would encourage you, if you're able to tap into that and see what's going on. This is the first time that, as far as I know, that anybody's ever done anything like this with the D-Light. So give that a try. And so that's pretty much all I've got to say. If there's any questions, I'll be glad to answer them at this time.
Thank you very much, Whit. Yeah, as is often the case, more questions have come up than answers. I'd be very interested to follow the story as it unfolds. Are there any, oh, excuse me, are there any questions or observations or comments or answers as to why there was that very low frequency oscillation towards the end of the day? Yeah, Martin, unmute and go ahead.
Yes, good evening, and thank you for the talk, but that was very, very interesting. I thoroughly enjoyed it, as propagation shocks are always very good. But really simple question, and was, did you actually carry out a control experiment, either prior or following the eclipse, to see whether the oscillations were present in a non-eclipse situation?
Yeah, I had looked at, I've been actually monitoring these stations for several years now, and I've never noticed that before. So those oscillations that you were seeing at the end there on some of those paths. I haven't noticed them, but I need to go back and look at my previous plots in more detail to see if they are actually there during normal operation.
It's quite interesting because the other thing I was puzzled about it, how long does it take for the D layer to sort of disassociate in the absence of sunshine? And I appreciate it's very, very localized compared with a D layer forming over half a hemisphere.
Yeah, was there a question there? I didn't get it.
Yeah, sorry. How long does it normally take for the D layer to disassociate, to break down in
Oh,
in these conditions?
Only the D layer along the eclipse path would be affected, and I would expect it to disappear pretty rapidly during during the darkness of the eclipse. But in terms of how quickly that would happen and how quickly it would return, that's a good question. I would think it would be more or less like the effects at sunrise or sunset.
Okay, thanks. I'm just puzzled about that. I did wonder what the impact of the eclipse would be. I suppose really the opportunity to re-experiment from people who are fortunate enough to be in the eclipse path tomorrow.
Yeah, that's really a good point though, because I would think that if the short paths, I believe that most of my reception was short path, if not all of it. And so if the eclipse had crossed a short path, I think it would have been more obvious. And so the long paths, the signal level was probably so depressed that any kind of D region or ionospheric effect would most likely just be washed out because the signal was just so weak to begin with.
Can I ask one more question? Yeah, it's very simple. I was always under the impression that for delay propagation to be effective, that both ends of the path needed to be in daylight. And obviously, you seem to suggest that's clearly not the case. And it's not really a question; it's just an observation. And that's really made me have a bit of a rethink about that because I always, like I say, I thought they had to be both in daylight. That's always.
Yeah, and that actually is not the case, at least in my experience, because all of those stations that I listed there, those 5 stations, at some point they are either one end or the other is in darkness, and I see them 24/7. They never go away completely. The signals do decrease when the path is in darkness, but they don't go away completely.
Oh, thank you very, very much.
So what's happening is the D region has dissipated. So that just means that the propagation path now has gone up into the probably the F region, which continues through the night.
Thanks, Whit. That's very, very helpful.
Yeah, thank you.
Thank you, Martin. Jonathan, you've got your hand up.
Hi, yes. Whit, that was a very good presentation. I really enjoyed it. I am a enthusiast, and I run a VLF receiver in northeastern Pennsylvania, and I have for the annular eclipse, I have observed the effect of both the the solar flare that occurred around the same time. I don't have those plots right now to share, but I would like to correspond with you over email, and I would like to share that, and we could have some discussion because what I saw with your plots, there were some really interesting results, and oftentimes with with these sorts of observations in VLF, it often raises more questions than answers, and that's why that I thought everything was really interesting. But do you have any plans on deploying more VLF receivers to?
Yes, I've had a kind of a long-term plan to put some up at Harp, which is about 400 kilometers away. It's a little higher latitude than I'm at. I haven't got that done yet. I did have so many projects going at Harp that I just haven't been able to get to it. But yes, I do hope to do more VLF.
Awesome. Is it okay if after this presentation or after this I correspond with you over email, because you're doing some really good experiments, and I think we could probably benefit with sharing our experiences and our results.
Yes, absolutely.
Awesome. Thank you very much.
Yep.
That's great, Jonathan. If there's any interesting conclusions from those discussions, do drop me a line, and we'll get you or Whit back again one evening to give you a opportunity to update us. Mark, I see you have your hand up.
Yeah, I was going to say that in 2015, I observed the solar eclipse that went over Spitsbergen and passed close to the UK. And I look at VLF stations over Europe and one on the east coast of the States. So they tend to be very short paths, sort of 200, 300, 400 kilometers. And what I did was to model how the amplitude should change when the eclipse passed over the midpoint of the path between my receiver and the transmitters. And what I found there is that there was a time delay of about 6 minutes between the predicted raising of the ionosphere and the actual effect. So to my mind, there was this 6 minute decay time of the ionization. And when I looked at various papers that other people had written about this, I found that they too had found a similar sort of decay time. Now, the eclipse on Monday, the path from my home here in the middle of England to Cutler on the east coast of the States, the path there crosses the total eclipse path. So I'll be interested to see what actually happens on that longer propagation path rather than these short ones, where I saw a very pronounced effect caused by the eclipse. What I wondered about your oscillations, because your paths are so long, whether this is just the amplitudes of all the modes, the waveguide modes, all crossing through zero several times. So you can imagine that as the ionosphere lowers during the day, on a short path, the phase doesn't change very much between the ground and the sky wave, but over a very long path, all these waveguide modes are going to interfere with each other. So I could imagine that you might go through zero amplitude several times. So it'd be interesting just to compare it from one day to the next to see what happens. But yeah, it'd be interesting that on Monday, if you all listen and plot from 24 kilohertz, which is the frequency of the one in Cutler, we'll see if anything happens on that long path.
Yeah, good luck with that. I can receive Cutler occasionally. For some reason, it's not. It doesn't come in like the other stations for me. But yeah, if you're able to get a good signal from that and have some effects, I would definitely be interested in seeing what happens. And I would expect that there would be maybe a signal increase during the eclipse, but maybe not. I don't know. I guess I'll have to wait to see what you get out of it.
Yeah, it's a bit complicated because the eclipse path sort of virtually follows the Great Circle path. Whereas when we had the eclipse before, we were quite often at right angles to the path. So it'd be interesting to see what this extended eclipse time will do to the amplitude.
Right.
So that's it, I'm finished.
Yeah, thanks, Mark. Any more questions or observations?
There's a Nick Everts on the chat. Nick, are you there? Can you pose your question, please?
Yeah, the link you gave for the video thing, can you pop that into the chat so we can save it, please?
Oh, yes. Yeah, let me do that right now. I should have it pretty handy here. And let's see.
Brilliant, thank you.
Okay, good. Yeah, yeah, give that a try. This is kind of a one-of-a-kind thing that's going on right now. And D-Light has been around for a while, but for an application like this, it's the first time it's been done. So I hope there's something cool that comes out of it.
Whit, are you aware of any professional observatories that have done similar observations?
No, I'm not. And I usually hunt around for things like that, but I haven't seen any notifications that anybody's doing this really, really interesting stuff. I guess there's no Nobel Prizes in it anymore, so nobody wants to spend any money on it, except me.
Well, if you get a prize, invite us to the party.
Definitely will.
Are there any more? Oh, excuse me. Are there any more questions for Whit? Yes, carry on, please.
Just to say thanks, Whit. A great presentation. I know we all enjoyed it.
Yeah, thank you.
Yeah, we will get you back again because this is one of those stories that's unfolding, and it'd be very interesting to hear any follow-up.
Well, Paul, you know, I've actually done some VLF observations on previous eclipses. I do remember the one in 2017. There was one in, I think, 2014 that I looked at. But this one in October was the first one where I'd actually taken a disciplined look at the paths and the potential for effects on those paths. So from here on out, now I'm gonna be a little bit better organized to do that kind of a thing. So hopefully I'll be able to report back to you sometime in the future about that.
Yeah, we look forward to it. We really do. Otherwise, that's just down to me to add my thanks to Whit for giving up his morning to share with us this evening. And just one minor comment from me before we sign off, and that is, if there's anybody on the call that is thinking they might be wanting to attend the European Amateur Radio Astronomy Conference next year, do visit the site and register your interest. I mean, it's really important for us at the beginning to have some idea as to as to what the interest would be. It would just help with planning at this early stage. I know it's over a year away, but we really want to put on a fantastic European conference. Already there are more than 40 people that have indicated that they're very likely to attend. So that's a great start, and the press release only went out last month. Anyway, good night, everybody, and we'll see you next month. Good night now.
Good night.
Thank you.